Sure.
Okay. In this presentation, I will introduce a paper. The title is Two-Stream Adaptive Graph Convolutional Network for Skeleton-Based Action Recognition. And this paper has been published in CVPR 2019. And the topic of the presentation is about the action recognition. I will introduce this paper from the following contents. First of all, I will give you some background information about the skeleton-based action recognition and the deep learning-based action recognition methods. Next, I will introduce some background methods about the spatial temporal graph convolution networks, and it is also be called STGCN. And next, we will come to the proposed methods. I will introduce these proposed methods from the overview and the adaptive graph convolution layer and the two-stream networks. Finally, we will land on the experiment and conclusion. So first, let me give you some background information about the skeleton-based action recognition. So the question is, what is skeleton of the human body? Skeleton data is a time series of 3D coordinates of multiple skeleton joints, which can be either estimated from 2D images by the post-estimation methods, or we can get the skeleton data from the multimodal sensors such as KeyNet. And here is a general pipeline of the skeleton-based action recognition use deep learning methods. We can see in this figure, the input is the video, and we can get the skeleton data from two aspects. First, we can use the KeyNet camera, or we can just send the video to the post-estimation methods, and then we will get the 3D coordinate of the human joints, and it is a sequence of human coordinates. And then we will send the data to the deep learning methods, for example, the RN, GCN, and finally we will our goal is to get the action category to classify the actions of human. And recent years, the deep learning methods has been widely applied in the action recognition task. The early methods are RN-based and CN-based. We can see in the below here are two example figures of the RN-based methods and the CN-based methods. For the first one, RN-based methods, it takes the skeleton sequence as a natural time sequence, a series of joint coordinate positions. It is similar with the speech input because it is naturally time sequence, and we send the skeleton sequence to the RN model and to calculate the loss, and we will finally classify the action. And about the CN-based methods, in order to explore the spatial information, some works has tried to use the CN-based methods to classify the action. And the first one, they treat the skeletal data as a 2D pseudo image, and then the 2D pseudo image will be sent to the CN model, and finally it will get the classification results of the skeleton sequence. However, due to the promising result of the RN-based methods and CN-based methods, it is still has some limitations to learn the features of the human body, because the skeleton is naturally structured as a graph in non-Euclidean space. However, the RN and the CN can't learn the features very well. So recently, the GCN-based methods has been proposed, and to model the structure of the human body. And we can see here is an example of the graph convolution. Compared with the 2D convolution, which has been used in most CM methods, it is obvious that the graph convolution is different. For example, the target point is this red one. However, in graph convolution, the contribution of the neighboring points are different. And here it is similar with the human body. Because, for example, if we want to calculate the feature of the feet, it's obvious that the leg will contribute more than the hand. And the first attempt of the graph convolution networks, it is the spatial temporal graph convolutional network. It also be called STGCN. It has been proposed in 2018 for the action recognition task. And here, I will introduce the STGCN as the background information, because this paper, the proposed method is the improvement of the STGCN. So we need to know some formulation and the background information about STGCN. First of all, we can see here is an example of the human topology of the human joints in spatial and temporal dimension. We can see that for the skeleton, it is naturally structured as a graph in a non-Euclidean space with the joints as vertex and their natural connection in the human body as edges. And it has been shown as the blue lines. And for the temporal dimension, the corresponding joints between two adjacent frames are connected with the temporal edges, and it has been showed as the green lines. And for the graph convolution, I will first give you the formulation of the spatial graph convolution. We can see the F represents the input feature map, and the F out represents the output feature map. The difference between the graph convolution with the normal convolution is that the sampling area of the convolution is different because the human body follows the non-Euclidean topology structure. So the B represents the sampling area of the convolution, and V represents the every joint of the human, and W is the learned parameter. And to make this formulation straightforward and easy to understand, we rewrite the first formulation to the below one, and we can see that the F also represents a feature map, and here A is a adjacency matrix. The shape is n plus n is n in, and it represents the connection and the connection of the n joints of the human body, and there are total n joints in the skeleton. So this matrix represents the connection relationship between every joint. And W represents the learned parameter. K is the kernel size of the spatial dimension. However, we can see from the this topology, there is some limitations and issues in the STGCN methods. The problem is that—
What's M sub K?
Okay.
What's M sub K?
So, Professor Han, you mean the K?
No, M. What is M?
M. M is determines the strength of the connection. It is similar with a tension mechanism.
But didn't you say W is weight vector? Doesn't that define the strength of connection?
No. W represents kernel. It is similar with the convolutional kernel, and it is the learned parameter.
Right.
Yeah.
So, and A already kind of determines what's connected to what, right?
Yeah.
So what does M do?
M. Okay, M represent. It is a tension map that indicates the importance of each joint, and it is also let me think about.
If it is not certain, maybe you can explain it with some following slides later. Okay.
Yeah.
Go on.
Yeah. Okay. So as introduced before, we already know that the topology is set manually. That is, the topology corresponds to the adjacency matrix. So it is fixed over our layers and input in samples. However, this fixed topology, it is difficult to capture the dependency between the two hands, since they are located far away from each other in the predefined human body-based graphs. So it is not very flexible. And moreover, in this STGCN, it just consider about the skeleton data and neglect the second order information, for example, the length of the bones and the directions. So in this paper, the author proposed a two-stream adaptive graph convolutional networks for the skeleton-based action recognition. And it is based on the STGCN model. Here are two contributions of the proposed methods. The first one is tries to propose a more flexible GCN to adaptively learn the topology of the graph for different GCN layers and skeleton samples in an end-to-end manner. And it is a data-driven methods can better suit the action recognition task. And the second contribution is that except the original skeleton data, it also explores to use the second order information of skeleton data. For example, the length of the bones, and by using these two kinds of data, the author has constructed a two-stream framework, which can bring the improvement for the recognition performance. And let's come to the adaptive graph convolutional layer. We can see that in the left one is the formulation of the STGCN for the spatial graph convolution, and the right one is the proposed graph convolution. We can see except the original adjacency matrix, we can see here the author also proposed another two part for the graph convolution layer, and A is same as the original one, so it is predefined and fixed according to the connections of human joints. And for the B part, it is similar with A part. However, there is no constraints on the value of B. It means that the graph is completely learned according to the training data. And it is trainable. We can see in this example figure, the orange represents the learned parameters. So the B part is totally learned by the input of the input. And for the C part, it is we first calculate the similarity in the embedding space. The input we can see here is a feature map, and we send them to a seed layer and a file layer to reshape the input feature map. And N represents the joint number, and C is the channel. T represents the time frame. And by reshape the input feature map, then we will calculate the similarity by multiply these two reshaped feature map, and then we will conduct the softmax, and we will get the CK. That is the last formulation, and it is also be considered together with the A part and B part, and the sum of the A part, B part, and C part will substitute the original adjacency matrix. So by introducing the B part and the C part, the author has made the graph convolutional layer adjustable according to the input, according to the different skeleton input. So it is totally data driven and more flexible. And next, the second contribution is the author just not just consider about the original joint information, and it also be considered that the born information for training. And he has proposed two stream networks. We can see here is the overall flow of the proposed methods. The input is the original skeleton sequence, and the J stream represents the joint stream, and B is the born. And born is calculated by the subtraction of the source joint coordinate and the target joint coordinate. We can see by introducing the born stream, and finally we concatenate the B stream result and the J stream, this J stream feature map, and finally we will calculate the cross entropy loss and get the classified action results. Here is the overall structure of the proposed methods. And next, we will come to the experiments, and I will show you some experiment results. The experiments are conducted on the two large-scale data sets. The first one is NTU RGB, and the second one is KeyNet. And the evaluation matrix is accuracy. And we can see here are the results which compared with the state of the art. We can see no matter in the NTU RGB dataset or the KeyNet skeleton dataset, the proposed method has achieved good performance. And even though just using the J stream or B stream, it also can achieve the competitive results. And
so how many categories were there?
For the NTU RGB dataset, there are total 16 categories, human action categories.
What were they?
There are many categories. For example, the kicking ball and play the phone and many of the daily actions.
Okay, thank you.
Okay. And next, here are some visualization of the learned graphs. We can see the first one is a visualization of the graphs for different layers. And from the left to right is comes from the third, fifth, and seventh layers. And we can see that from the with the layers going deeper, the learned features can be they will get a more global vision of the graph. And in this figure, each circle represents one joint, and the sides represent the strength of the connection between every joint of the model. And for the second one, it is a visualization of the graph for different samples. We can see for different samples, the proposed methods, proposed model can learn the different graph. And for the ablation study, we want to show the effectiveness of the area components of the proposed methods. We can see that compared with the STGCN, the proposed methods can get a better performance accuracy. And we can see that when excluding the A part, B part, or C part, there are performance drop, and which has shown the importance of the proposed adaptive graph convolution. And here, the next is the ablation study for the two streams. And first, we exclude the B parts, and here is a obvious drop of the performance, and similarly for when we excluding the J stream. And finally, we land on the conclusion. So in this
can you go back 2 slides?
Yeah.
Another one. If you go back one more, okay, here. So these are using 2 different data sets, one for NTU RGBD, and the other one is Kinect, right?
Yeah, yeah.
And so for Kinect, it's top 1% or top 5% accuracy, right?
Yeah.
Well, and on the NTU, I might have missed your explanations about the accuracy performance. What is X sub or X view?
Okay. It is the common use when we testing the action recognition model with the NTU RGBD dataset. It is cited by the original author of this dataset. X subject represent. First, I need to give you some background information about the NTU RGB. It is the dataset conducting by 40 different volunteers, and they conduct on every second for every action by different subjects, and the X subject represent we train the model with subject 1 data, subject 1 and subject 2 data. However, we test the test set is the same action but conducted by another subject, which has been not get involved into the training process. This is a cross subject setup. It means the training set, and the testing sets, the skeleton comes from the different people.
The distribution may be different.
Yeah, Yeah, maybe different.
So that's X sub. What about X view?
X view means the NTU RGBD dataset are simultaneously shooted by 3 KeyNet camera, but from the different angle. The volunteer is 1, but at the same time there are total 3 camera which are sighted in 3 direction. And the X view means we use the direction 1 and direction 2 as the training set, and the direction 3 skeleton data will be used for the testing. So the training and testing set skeleton are collected from the different direction.
But wouldn't the data be given in terms of the skeletal joint locations, or that's just fed as Kinect data raw?
It is processed data. It's just the frame by frame, and for every frame, there are 3D coordinate of the human skeleton. There are total 25 joints of human.
Okay.
And yeah.
So in the case of X view, there may be some bias then, right? Because you're looking at it's obtained from another camera.
Yeah. The direction, the angle is different.
Okay. All right. And so it seems that table 3 shows, well, it seems better performance compared to Kinect data set.
Yeah.
So for Kinect, how is it different the way the data was acquired?
So you mean the difference between these 2 data sets?
Yeah. Because it seems that there's a big difference of the performance. Right?
Yeah. I have seen many papers which has conducted experiments on these 2 data sets. However, every paper in every paper, the performance in Kinect is quite low than the NTU RGB dataset. However, my recent experiments are concentrating on the NTU RGBD, so I haven't done the experiments on the Kinect dataset, so I'm not very clear about the second dataset, how it's constructed and the exact difference.
Okay. All right. Well, thank you.
Okay, thank you. And for the conclusion, we can see the proposed method has proposed a novel adaptive graph convolutional neural network. And compared with the STGCN, it is more flexible and data-driven. It can increase the flexibility of the graph convolutional network, and it is more suitable for the action recognition task. And furthermore, the proposed methods has proposed to use the bone data for training, and it can also achieve the improvement of the performance, and it can further enhance the accuracy of the action recognition. So this is the end of my today's presentation. So if you have any questions, just feel free to ask. So is there any questions?
Okay, so let's go back to the conclusion.
Yeah.
Okay, so overall, I'm just curious about the trend of, say, graph convolution neural net based, skeleton, learning system or action recognition. I'm just curious because if it is based on I mean, the structure is a graph CNN. So graph is there, graph structure is there, but it's based on, and I think you showed something like RNN somewhere in between. So I'm just wondering if the structure is very similar to how the speech processing or language or NLP takes place. Maybe you could do some use some transformers instead. So I'm just curious if you also bumped into any papers having to do with using transformers for skeleton-based action recognition.
Actually, recent, yeah.
So that's one question. And the other question is about the data set. You mentioned about two types of data set. These, when these skeletons are taking place, I presume that it captures, person making motions. And I'm just wondering how diverse the motions are. For example, in terms of like different perspective angle. Because I'm sure that the performance will probably very much influenced by how much this person makes these motions, whether the motions are taking place in front of the camera, like directly, versus like all the motions are taking place by the perspective looking from the side.
Yeah.
So that's another thing I think if you can find out about the data set, whether the data set does indeed have all these various perspective angles.
Yeah.
Have you done this? Is there any code for this, by the way?
Professor, you mean so
for this
you
particular
want
paper?
this paper? Oh, sure.
Okay,
there,
code is good.
Yeah,
so
it's available.
Okay, you ran the code as of yet, or you're not there yet?
Okay, I will try this code. As for the first question, actually, I also read many papers about the GCN for action recognition, and I haven't seen the GCN papers which has also using the transformer technique, because in my opinion, maybe I think even though the skeleton sequence is time series data, however, the GCN model may be not very suitable for the combination of the transformer. But I do see about 2 papers which has been used for action recognition using the RNN and combined with the transformer technique. So I will follow this trend, and maybe there are some chance to compare the GCN with the transformer, because for the action recognition, the most recent proposed methods are based on GCN, and GCN is obviously superior than the RNN-based methods because it can naturally capture the topology of the human body. However, for RNN, it can't model the spatial relationship between human joints. So I will focus on it and see if there is opportunity to combine these 2 techniques for this task.
Okay. How about a data set question?
This set question. You mean the different angle may
Right.
have
Let's go
some.
back to the previous slide where you have the data set.
Yeah.
The NTU and the kinetics. Have you looked into the type of data set they have here? Do you have a better feel for it? For example, like, you know, how, what's the size of the data set, for example?
For the
How many
NTU,
samples? How many? Yeah.
there is total about 50,000 action clips in the NTU RGBD.
Okay, so 50,000 actions, and each action is about roughly how many seconds?
It's about no more than 10 seconds.
Okay, and these are samples of the same person or like different person? And also, like I said, like, does it have like different angular view?
Yeah. There are total 40 volunteers, humans performing.
Okay, 40%, I see.
Mm.
And I guess various motions, right? Like not just stretching or, you know, like waving, but also, I don't know, like just motions like sitting down and, you know, walking and so forth, right?
Yeah.
All these various motions.
Yeah.
Okay, so are these the only data set that you know of, or is there like more?
This is the in this paper, they just use the NTU RGBD. Actually, later there is an extension of the NTU RGBD. It is called NTU RGBD 120. It is 2 times bigger than NTU RGBD, and
Okay.
the extension is currently the biggest scale data set for action recognition.
Oh, I see. So, and this is publicly available.
Yeah, available.
Okay. Okay. I was just curious, you know, about the data set, the extent of data set that could be made available for the lab.
Yeah.
And so I guess overall, the reason I'm asking all these things is for the actual, you know, application, whether or not you could actually use this for real world application.
I
What
understand.
do you think?
Yeah, actually, for the project, I also use this data set because it's large enough.
So you don't think that you know, the lab would need lab's own data set to you know, so that you could have a larger or better fitted model? Or do you think this would be enough?
I think maybe for some specific action categories which are not be involved in the NTU RGBD, maybe there are some requirements of the specific actions.
Okay, good. So this would be good and suitable for maybe paper purpose, right? Just to address how you could improve overall performance by maybe modifying or using some, you know, slightly different type of structure. But always we have to think about real-time application.
Yeah.
Right?
Yeah.
Okay, good. Good.
Okay, thank you.
Very
Professor.
useful.
So is there any other questions?
네, 수고했습니다.
Thank you for the
수고하셨습니다.
presentation.
감사합니다.